Yeah, so welcome everyone to this week's Physics Meets ML. We're very happy to have Vishnu Jejjala here talk today about machine learning as a discovery tool in hep-th. Vishnu is a professor at the University of Witwatersrand in South Africa, and his research background is in string theory, where he's worked on a numerous number of topics. This includes black hole thermodynamics, particularly in the context of holography, holographic duality. And in the past years, one of his interests has been the application of machine learning in high energy theory. And so we're very excited to hear his perspective today. And we're very much looking forward to your talk. So please, Vishnu.
Okay, great. Thank you for the invitation. I'm happy to speak here. So welcome to my kitchen. I'm happy to see a lot of old friends and new ones on the list of participants. So I tried to make this talk accessible to a broad audience, but please ask questions if I'm being confusing. As I'm a physicist and not a computer scientist, I invite the views of machine learning experts who can tell us how to do various things better. Right, so I'd like to discuss how to change the title preposition to a verb. I'd like to have machine learning be a discovery tool in the next iterations of this talk and similar talks. So we're going to proceed with some case studies where machine learning has proved useful and may indicate the existence of analytic formulas for us to discover. So broadly speaking, this area is maybe called mathematical phenomenology. We note patterns and we look for an explanation. The canonical example of this may be mirror symmetry. So the logo for physics intersects machine learning is a Calabi-Yau manifold. So Calabi-Yau manifolds are the geometries that are associated with string compactification from 10 dimensions down to 4 dimensions. So initially, Voffler noticed that two Calabi-Yaus give the same physics. And Green and Plesser and Candelas, Linker and Shimerick, and Candelas, Bella Osa, Green and Parks were able to solve problems in enumerative geometry using the idea that for every Calabi-Yau, there's a mirror pair. And if you look at the plot, the shield that appears, there's a mirror Calabi-Yau for each geometry in this plot. So mirror symmetry originally was phenomenology. It was an observation on the space geometries associated to this problem in string theory, how to go from 10 to 4 dimensions. But mathematicians, given Tall, Yau, and collaborators, were able to make these statements on a more formal footing by using the insights of physicists. We're trying to use machine learning in a similar manner. We're using machine learning to make phenomenological observations, and then hopefully these phenomenological observations will lead to analytic results. So, so far in high energy theoretical physics, machine learning is a black box. It gives approximately correct answers to a large class of problems, but we'd like to use machine learning as a proper tool in order to advance our own area. So in some cases, this may be filtering interesting geometries to study, for example, in the Calabi-Yau context, for certain aspects of string phenomenology that we might like. But we'd also like to understand at a deep level how this all works and how the predictions of these machine learning models can be translated to something which is a formula that lets us study problems that we're interested in analytic detail. So with the Calabi-Yaus, my collaborators and I started playing with the utility of machine learning in this context. And these Calabi-Yaus are characterized by certain geometric properties. As real manifolds, these Calabi-Yaus are 6-dimensional. This is going from 10 to 4 dimensions using these compactification schemes. So because you have a 6-dimensional manifold, this manifold can have 2-dimensional holes, 4-dimensional holes, 3-dimensional holes in them. And there are topological invariants that count the number of holes of each dimension. So given a certain class of roughly 10,000 of these geometries, we're able to learn how many holes the geometry has. The traditional way of doing these calculations, sequence tracing in algebraic geometry, is rather involved. And if you put it on a computer using computational algebraic geometry, these algorithms are doubly exponential in time. Whatever the machine's doing, it's doing it in polynomial time. So this indicates maybe that there are better ways to compute in algebraic geometry in this context. So that would be one thing that machine learning may eventually teach us, what the clever way of doing these calculations are compared to the rather complicated ways that we have at the moment. So in this talk, I'll discuss two other case studies. One involves knots, and the other involves a theory of particle physics called QCD. So the knots you can think of as a circle embedded in a three-sphere. And these knots have recently been in the news. Lisa Piccirillo solved an outstanding problem in knot theory analytically. And the question was, is a particular knot with 11 crossings called the Conway knot smoothly slice? What this means is, does this knot in S3 bound a disk in a four ball? The answer turns out to be no. There's a question that has perplexed mathematicians for a long time. And Mark Hughes, a long time ago, well, 2016, 5 years ago, tried to examine this problem with machine learning. And when he attempted this machine learning, it turns out that the machine also didn't know. It was roughly saying, yes, it was smoothly sliced 50% of the time, and no, it wasn't smoothly sliced the other 50% of the time. So analytic methods still have their place, of course. QCD is a theory of how matter is put together. So we learned in high school that, that the substructure of atoms consists of a nucleus with shell of electrons around it, and the nucleus itself was made of protons and neutrons. Well, the protons and neutrons are also made of fundamental particles. These fundamental particles are quarks and gluons. So understanding the structure of how these elementary building blocks are put together is a subject of QCD, and we'll use machine learning in both of the contexts of knot theory and QCD. So again, please ask questions wherever they're necessary. All right, so let's start talking about knots. So here are some examples of knots. As I said, knots are circles embedded in three spheres. So the simplest knot is the unknot, but if you include crossings, you have the trefoil knot, the figure eight knot, the cinquefoil knot, and three twist knots as some of the simplest knots that we encounter. So the thing is that you can draw a knot lots of different ways. So these are two different ways of drawing the unknot. One's due to Thistlethwaite, one's due to OCI. If you look at these things, it looks knotted. It doesn't look like an unknot. So it's a question of how do you distinguish one knot from another when, say, given a picture of a knot. What can you possibly do in order to figure out which object you're actually talking about when all of these being made to look very complicated? So the thing to do is to invent topological invariants. These are independent of how the knot is drawn, and you can use this to characterize the class of knots that you're studying. So one topological invariant is called the Jones polynomial. It's defined using something called the Kaufman bracket. But it turns out there are cleverer ways of computing the Jones polynomial. One technique to compute these polynomial invariants for knots is using quantum field theory. So that's the entry point for physics into a mathematical problem. So you can ask, what is the simplest non-trivial quantum field theory? In 3 dimensions, this turns out to be a theory called Chern-Simons theory, and it's topological. It means that the metrical structure of your geometry doesn't really matter when studying the physics of this theory. So we focus on topology instead of geometry. And physics is famous for the spherical cow approximation, where we treat cows like spheres. So the topological invariant, you compute what are called correlation functions in quantum field theory. These correlation functions are independent of the metric on the manifold. That is to say, they're independent of how you measure distances on your geometry. So in Chern-Simons theory, the natural operators are called Wilson loops, which you consider are path-ordered exponentials of the fundamental field in Chern-Simons theory along some curve. And you compute this in some representation of the gauge group associated to this quantum field theory. So the gauge group encodes the local symmetries of the theory. So The knot invariants are computed by taking the curve along which you're integrating to be the knot in S3, for example. And this description of this theory is very rich. We've learned a lot about both mathematics and physics by focusing on this very simple quantum field theory. The action of this theory has an integer k, which is called a level. This is quantized, and it basically needs to be quantized. It needs to be an integer in order to make the theory be invariant under large gauge transformations. These are gauge transformations that are not homotopically connected to the identity. So if you're not an expert in quantum field theory, I just want the take-home message here to be that there's a quantum field theory that lets you compute knot invariants. And these knot invariants distinguish knots from each other. So Witten in the late 1980s won a Fields Medal in part for the observation that these Jones polynomials can be computed in Chern-Simons theory. Essentially, you compute some polynomial and some parameter q. Q is either 2 pi I over k plus 2. K is the level of the Chern-Simons theory, and the plus 2 is because the dual Coxeter number of SU2 is 2. It's a shift. So in addition to the Jones polynomial, another invariant for a class of knots called hyperbolic knots turns out to be the volume of the knot complement. So if you take the sphere on which you embed the knot, you excise out an epsilon neighborhood around the knot, what's left over is a knot complement. It turns out that for hyperbolic knots, the complement has a Riemannian metric with a constant negative curvature. So almost all knots up to 16 crossings, and there'll be lots and lots of these knots, almost all of them are hyperbolic. All but 31 of them turn out to be hyperbolic.
Question?
Yes.
Yeah, sorry, I have a question. So I didn't quite understand this idea of the volume. K, the knot is a one-dimensional object inside a three-dimensional thing, so it will have measure 0. So what do you mean by the volume of the complement?
I mean, if you take a neighborhood of the knot and you excise it, and you take what's left over, it's some hyperbolic manifold with a metric on it. You take that geometry and you end up decomposing it using ideal tetrahedra. That will turn out to have a finite volume.
Okay, so when you excise a small volume around your knot, so the final volume will depend on the size of the excision, no? So how big you make?
You take epsilon to 0. But yeah. After you take epsilon to 0, you take what's left over and you put a metric on it. That metric turns out to be a hyperbolic metric.
Okay, so the metric was not existing on S3. It's a metric which is dependent on the knot itself that is being excised.
Absolutely, yes.
Thank you.
So Thurston noticed that this was a knot invariant, that regardless of how you draw the knot, you get the same result for the hyperbolic volume. So this is another such invariant. It turns out that the Jones polynomial and hyperbolic volume are connected. And that's one of the results that machine learning teaches us. So in addition to the Jones polynomial, there are so-called colored Jones polynomials. Instead of taking the trace in the fundamental representation of SQ2, you take the trace in some other representation of the SQ2 gauge group. In the limit where the dimensional representation goes to infinity, the logarithm of the Jones polynomial with this n color evaluated at a primitive root of unity gives you the volume. This is a conjecture to Kashayev, Murakami, and Gukov. It turns out that this conjecture applies in the n goes to infinity limit, and you can test this for simple knots. So one of the simplest knots for which we can do this test is called K0. It's an 18 crossing knot. I've shown a picture of it. This knot is simplest not in terms of it having a small number of crossings. It's simplest in the sense that a very small number of ideal tetrahedra are needed to perform the triangulation I talked about. As you can see, the small values of the color in this plot are not really a very good approximation to the actual volume of the knot complement. The actual volume of the knot complement of this knot is 3.47 something, whereas the initial values are 5 something. It's only in the n goes to infinity limit that you see some convergence to the actual value. And in fact, even at n equals 250, convergence is not really that great yet. So it's really phenomenal that if you just know the Jones polynomial, the simplest colored object here, you can predict the volume with very strong accuracy. Okay, so the Jones polynomials that I showed you earlier, they have integer coefficients. Why do they have integer coefficients? It turns out those coefficients are dimensions of things. These dimensions of things can be computed using an apparatus known as Kovanov homology. Initially, Nathan Dunfield noticed that for a class of knots called alternating knots have an overcross and undercross alternating between each other when you draw the knot. If you take the Jones polynomial of such knots, evaluate it at -1, the logarithm of this is proportional to the volume. That was Dunfield's observation. Kovanov, who developed this apparatus of homology, determined that if you take the rank of in this homology, that is to say you sum the Hodge numbers, that's also proportional to the volume. An analytic result is called the volumish theorem. It puts a bound on the volume of the knot complement to lie between a lower bound and an upper bound determined by the coefficients that appear in the Jones polynomial. The coefficients that appear in the volumish theorem are the penultimate coefficients on each side. So that was the state of things initially. And here's a plot. If you take the volumish bound, it gives you an interval, and you select some number within that interval, and you compare this to the volume, you find that for the class of alternating knots, about 111,000 of them, up to 15 crossings, the error is about 107% in matching this number chosen from this interval uniformly with the actual volume. So if you look at Kovanov homology and you look at the Kovanov rank and compare that to the volume, the error is about 5%. And this is for 196,000 knots, about 62.6% of the data set we have for knots of hyperbolic type at up to 15 crossings. So I presented to you 6 characters in search of an author. I claim the author is a neural network. So this is an absurdist play by Luigi Pirandello in the 1920s, and it seems very appropriate that if we're mathematicians or physicists just fiddling with things, the absurdity of finding an answer using a machine is compelling somehow. So the machine, of course, is a feed-forward neural network in this case. We essentially adapt the original ideas of Rosenblatt in the 1950s, the Navy Research Lab, and we use Mathematica to implement this neural network. So we're going to use a very simple neural network. I got ahead of myself. So the neural network feeds in the Jones polynomial and compares and tries to learn the volume. So the Jones polynomials are represented as 18 vectors. The way we do this is it's a polynomial, so it's got a minimum degree and a maximum degree and a bunch of coefficients. And we pad with zeros as necessary in order to get 18 vectors. We have a simple two-layer neural network, 100 neurons in each layer, and we use logistic sigmoids for the nonlinearities in the hidden layers. Doing this, if we train on 10% of 313,209 knots up to 15 crossings, the prediction on the remaining 90% has an error of 2.45%. And if you run the neural network 100 times, the error doesn't change very much. So this is a phenomenal prediction, and it suggests there is some structure in these knots that that's embedded in the Jones polynomial. The neural network is able to distill. So more advanced versions of Mathematica, the latest iteration, reduces the error to 2.36%. This is in fact about as good as you can do. And I'll explain why momentarily. As well, the training even on 0.1% of this data set, so you use roughly 300 knots out of 313,209 to develop your network, and you predict on the other 99.9% of knots in your database, already this error improves the result from Kavanagh ranks. So Kavanagh homology is a very complicated apparatus. A simple neural network does better at some level. So this is this indicates, at various fractions of training how well the network performs. As well, we can look at the spectrum of the weight matrices and the bias vectors and so on, and we notice that there are certain properties of these neural networks that are somewhat universal. The eigenvalues roughly follow the same sort of shape, and it turns out that one of the eigenvalues in the second layer is always going to be a negative real number, and this is some generalization of Perrin Frobenius that establishes this kind of result. So we've seen that if the neural network makes a prediction f of j, the volume is actually f of j plus small corrections. It gets things pretty much right. The reason why there are these small corrections is the Jones polynomial itself doesn't uniquely identify a knot. That is to say, two different knots whose volumes, whose knot complements have different volumes, might have the same Jones polynomial. In fact, in our data set of 300 and some thousand knots, there are 174,619 unique Jones polynomials in this data set. So the average spread in the volumes for knots with the same Jones polynomial is about 2.8%. So our neural network is capturing results up to that error, basically. The fact that different inputs give different, the fact the same input, the same Jones polynomial, gives different outputs may be an intrinsic mitigation against overfitting effects that one might encounter. So I showed plots for knots up to 15 crossings, this data set of about 300,000 knots. The same story applies in the full data set with 1.7 million knots up to 16 crossings. So what's going on? Why are things working the way they are?
There's a question in the chat.
Yes.
So this is from Jared Sloan. He's asking whether you have also analyzed Jones polynomials with sequential instead of feed-forward neural networks. And if so, was there any improvement?
We have not, at least not to my knowledge. Maybe my collaborators have. I don't know what the result would be. It's an interesting suggestion. Anyone else? Okay, so in some sense, the volume is a classical object. The Jones polynomial is a quantum object. So it's interesting that a quantum object is predicting something classical. It would be interesting to understand this from a fundamental perspective of Chern-Simons theory to understand why this happens. Another sort of mystery is that the volume conjecture has an absolute value when you take a logarithm of the colored Jones polynomial in the infinite color limit. If you remove the absolute value, instead of getting a real number, you get a complex number. The real part of that complex number turns out to be the volume, and the imaginary part of that complex number turns out to be what's called the Chern-Simons invariant. So at some level within the volume conjecture, the Chern-Simons invariant and the volume of the knot complement appear on an equal footing. Can we try to learn the Chern-Simons invariant in the same way? The answer turns out to be no. If you try the same protocol for training and prediction, you get essentially random garbage when you try to learn the Chern-Simons invariant. This might suggest that there's a need for underlying homology theory in order to make these sorts of predictions. And we found success in computing homologies in different contexts. For example, the Claude-Biot topological invariants I talked about are also essentially capturing what's called de Rham cohomology. Andre Lucas and collaborators have looked at line bundle cohomology, and they've abstracted exact formulae based on these sorts of investigations. We ultimately want a not machine learning result concerning knots. We want something analytic. And let me discuss some ways that we're approaching this problem. So for one thing, why is it that Jones polynomial n equals 2, the simplest representation of SQ2, knows about this infinite n limit? And if you plot the next colored Jones polynomial, you have a data set of about 11,921 of these, and you compare the evaluation of what's in the left-hand side of the volume conjecture at n equals 3 to n equals 2, you find that they're roughly quadratic. So it may be the colored Jones polynomials have some structure that's already embedded in the simplest case of the ordinary Jones polynomial. And it might be the machine's just picking this out. So if you ask which parts of the input are the most important, it looks like initially, this is an 18 vector, remember, the first two entries are the maximum degree and the minimum degree, and the rest of the coefficients. It looks like the neural network is focusing on the degrees and also the coefficients at the very end. This might not be a surprise because the volume-ish theorem I talked about looked at the penultimate coefficients. So that turns out not to be the case experimentally. If you drop the degrees, you find that the results are unchanged. The degrees are necessary to reconstruct the Jones polynomial, the topological invariant we're discussing, from the input. If you just ignore the information you need to reconstruct the topological invariant and just feed it the coefficients, the performance is unchanged. You get 2.36% error. The volume is determined, as far as the neural network is concerned, only by the coefficients in the Jones polynomial. Remember, these coefficients were dimensions of things in this Kovanov homology. If you look at how the coefficients change in these Jones polynomials compared to the volume, you also find some analytic trends, at least. If you compare the coefficients, so C plus or minus 2 takes the coefficient 2 from the endpoint at the minimum degree and 2 from the endpoint in the maximum degree. C plus or minus 3 takes 3, etc. You find that these scale as powers of the volume that roughly increase by 0.5, at least as you continue with the plots. So there may be quite a bit of information containing these coefficients that enables the network to reconstruct the volume. And we're looking for analytic approaches that accomplish exactly this. So the initial work was done by Arjun Kar and in collaboration with Arjun Kar and Ankar Parikar. Ankar was a postdoc at Penn at the time. He's now at Stanford. Arjun was a student at Penn at the time. He's now at the University of British Columbia. The more recent work we're doing, trying to disentangle how these networks are performing and the observation that the degrees don't matter and just coefficients do, is done in concert with my student, Jessica Craven. She's directly responsible for many of these new results. So our paper on our new observations is forthcoming, hopefully later this month. Okay, so this is a natural place to pause. I discussed my first case study. Before I move on to QCD, are there questions? Okay, I'll take that as permission to move on. So we'll look for masses of the kind of excitations we encounter in QCD, and we'll see what machine learning can teach us in this context. So let me say a few words about quantum field theory for the non-experts. For the experts, I apologize for the oversimplification of things. So a field has a position at every point in space-time. A classical field might be temperature on the Earth or pressure on the Earth. Every point on the Earth has some pressure and some temperature. Particles in quantum theory are excitations of these quantum fields. To define a quantum field theory, you specify the fields and how they interact. So for example, I've shown Feynman diagrams for tree-level interactions between electrons in the theory of quantum electrodynamics, QED. Essentially, these electrons and positrons interact by exchanging photons. The The diagram on the left you can think of as the origin of the Coulomb force explains the repulsion of like charged particles from each other because the interaction exchanges the photon that sort of drives them apart heuristically. The second diagram shows an electron and a positron annihilating, forming a photon, the photon branching off into an electron and a positron again. So these interactions are embedded into the structure of the theory, and once you know the fields in the theory and how they interact, you have some description of the physics, and you can make computations with this. For example, you can compute cross sections for processes, and compare to experimental cross sections, you find tremendous agreement. The quantum field theory, which describes the fundamental forces we encounter, is called the Standard Model. It's not a very creative name, but it works. So if you take an experimental value of something called the fine structure constant in QED, and you measure it, and you compare it to the theoretical value using a very, very complicated perturbative calculation in QED, you find that the two agree to many, many decimal places. In fact, this is the best agreement between theory and experiment in the history of science. So it's a very profound theory that we have in order to accomplish this kind of agreement. Standard model describes everything we've seen so far except for gravity. There's good reason to believe the Standard Model is incomplete, but the LHC, our best particle accelerator, has not seen any beyond the Standard Model physics today. The good reasons why we think it's incomplete is because of things like the universe being made of matter instead of antimatter. We need a process called, well, you need CP violating processes, they're called, in order to get this asymmetry. While the Standard Model accommodates CP violation, it doesn't accommodate enough CP violation in order to present this difference between matter and antimatter in the very early universe that eventually produced a universe made mostly of matter. The Standard Model also doesn't accept gravity. So in order to incorporate gravity, we need to go beyond the framework of quantum field theory. In any case, it's a very, very successful theory. I'm going to focus on one sector of this theory. The sector is called QCD. It's a strong force that explains how protons and neutrons are constituted. This part of the Standard Model is the least understood part of the Standard Model in the sense that there's a phase of this theory that we don't have analytic control over. Gross, Wilczek, and Politzer won the 2004 Nobel Prize for an observation they made in 1973 called asymptotic freedom. This observation is that if you look at how the interaction strength in QCD changes as a function of energy, you find that very high energies, the strength becomes very, very weak. So effectively, at very high energies, quarks, the particles that carry the colored charge of QCD, become free. At low energies, below what's called the confinement scale, lambda QCD, this coupling blows up and the theory ceases to be perturbative. So we don't have a good perturbation theory that controls the physics of this theory. This regime, in contrast to asymptotic freedom, is called infrared slavery. In this regime, we see states like protons and neutrons. These protons and neutrons don't actually carry the colored charge of QCD. They're color neutral particles. So they're a bound state of quarks and gluons in QCD in order to excise this color charge. They're singlets of SU3, in other words. So we'd like to understand a little bit about masses for these colorless particles that we see at low energies. So my students recently in my mathematics course, my undergraduates, they worked out the representation theory that you see on this slide. So if you take quarks and antiquarks, you can combine them to form what are singlets, what are called singlets. So they're colorless representations of QCD. Similarly, if you take 3 quarks or 3 antiquarks, you also encounter singlets. So the particles that are combinations of a quark and an antiquark that produces a singlet are called mesons, and 3 quarks or 3 antiquarks are called baryons. The meson in QCD you can think of as being held together by gluons. This thing is sometimes called the QCD string, and there's a deep connection between the origins of string theory historically and investigations of QCD. Okay, so most of a hadron's mass, so hadrons are these mesons and baryons. It's a superset of all these guys that you encounter in QCD at low energies. Most of the mass comes from strong coupling effects. They're not coming from the individual quarks and gluons themselves. They're coming from the physics of this confining phase of this quantum field theory. So what can we say analytically? This SU3, this 3 is called the number of colors. We call it n. If you take n to infinity, if you take n large, you introduce 1 over n as a new perturbative parameter in your theory. You can do some analytics in this new perturbative parameter, 1 over n. So Witten noticed that in large n, the baryons are what are called solitons in the meson spectrum. The mesons are essentially free particles with couplings that scale like 1 over n, and the baryons are like monopoles with masses that scale that are order n. So they're very, very heavy compared to the mesons in this large n limit. So we'd like to see whether we can exploit this at n equals 3 to say something about real-world QCD excitations we've seen in real-world QCD using this framework in mind. All right, so we looked at our particle data book, and we noticed there are 196 mesons and 43 baryons. The mesons have integer spin, they're called bosons. The baryons have half-integer spin, they're called fermions. And we look at the particle properties of mesons and baryons. It turns out that this data set we have of mesons and baryons, we know we've measured quite a few things. We measured various quantum numbers associated with these particles. These quantum numbers we measured include isospin, angular momentum, and parity. There are other measurements, G parity, charge parity, width, lifetime. These things are not complete in this data set as far as measurements that people have made. So we don't include that in our analysis. We just focus on I, J, and P, which we have for all of the mesons and baryons that we're studying. You'll notice this is small data. We have 196 mesons, 43 baryons. Naively, all of this may not work. Turns out it works, otherwise I wouldn't give this talk. So we're going to optimize our architecture by training with the mesons. So Witten, remember, said that mesons are some almost free theory, and baryons are excitations in this almost free theory. So we'll try to learn mesonic data and predict baryonic data in real-world QCD. So that's the idea. We've seen more exotic resonances as well. Pentaquarks have been discovered by LHCb, an experiment at this Large Hadron Collider. And there have been inklings of tetraquarks, although they're not strong enough to say we've had a discovery yet. So Koji Hashimoto, in the same seminar series, gave a beautiful talk on the applications of machine learning to what's called ADS QCD. So it's a description of quantum chromodynamics, the strong force that we're studying in terms of the physics of anti-de Sitter space, one of these geometries that are ubiquitous these days in string theory. And he's able to predict various quantities in QCD by training on different sorts of data that are independent of what's being predicted. So we'll try to do something similar in this story. So again, we'll use neural network. We'll use the hadrons as 13 vectors. These 13 vectors essentially describe the quark composition of these excitations. So there are 6 species of quarks: down, up, strange, charm, bottom, and top. And there are also anti-quarks for all of these quarks. Top quarks decay too quickly in order to be found in bound states. So we can look at the lightest 5 quarks: down, up, strange, charm, and bottom. And we include these isospin, angular momentum, and parity quantum numbers. And since we have a very small amount of data, we'll use as simple a neural network as possible in order to try to see whether we can interpret what we're finding. So we use one hidden layer network with 50 neurons in the layer. Again, they're just a sigmoid function. We can also use Gaussian processes for this problem. So essentially, the Gaussian process was invented not too far away from where I am right now. Danny Kriege in Johannesburg. Johannesburg was established in the late 1880s as a mining town. And the Witwatersrand Reef Complex, which shares the name of my university, They dug bores and they took these samples and they saw how much gold there was in these samples. And they tried to infer the distribution of gold deposits based on this sampling. In order to do this in a thesis, Danny Krij invented the Gaussian process, independently of Wiener and Kolmogorov, who stumbled upon the same thing in more mathematical contexts. And recently, of course, it's turned out the infinite width limit of a single hidden layer network is also a Gaussian process. So in our process, we'll use different kernels. We'll use the square exponential kernel and the rational quadratic kernel. And essentially, the number of parameters are sigma f, sigma n, alpha, and the elements of some diagonal matrix, lambda. So the diagonal matrix is defined by the size of your input. So in our story, we'll have 17 parameters. And we'll use this Gaussian process to maximize the log marginal likelihood computed in this way as a relative entropy, basically. The fact that we're inverting matrices makes this ideally suited to small data as opposed to big data in some sense. The vectors are small enough that we can invert these matrices. And we can use these matrices in order to make predictions with mean invariance for the output. So we're trying to predict the masses of these excitations based on the input. So given some prior, I've got some sine pi over 2 over times x function here. In the prior, we essentially pick the dash curves are selected from some Gaussian process with 0 mean. And after optimization, after we employ the Gaussian process, we get some posterior, and with 99% confidence, we draw various curves within this posterior. So the variance in the prediction increases as you move further away from the data points that you have. So training on 80% of the mesons, we find that the neural network has a 13% error in predicting the mass. We're excluding the pions. The pions arise from something called spontaneous symmetry breaking, or the chiral symmetry in QCD. They're pseudo-Goldstone bosons that have low mass, so we exclude them in computing the errors. But for the rest of the particles in blue, we find that the neural network makes very good predictions. I'll tell you about the points in orange very soon. So these are the mesons. This is a training set that we're using. Now we take this neural network trained on mesons and apply it to the baryons. And when we do this, we compute the mass of the baryons with less than 10% error. The baryons sort of cluster in different groups. The group at the bottom is comprised of down, up, and strange quarks. The group in the middle includes charm quarks, and the group at the top includes the bottom quarks. And we can, make predictions, and we compute means and variances and so on. The distribution of what is predicted over various trials follows a normal distribution. So it's appropriate to use standard deviations in order to describe the errors in our analysis after 1,000 runs. Okay, the orange dots correspond to what's called the constituent quark model. The constituent quark model computes the QCD binding energy of a particle. It's the amount of energy you need to add in order to spontaneously emit a meson containing a given valence quark. The constituent quark model essentially assigns an effective mass to each of the species of quarks we encounter, and you just add them up basically in order to get the prediction of the constituent mass quark model for the mass of these mesonic and baryonic excitations. So on the mesons, the neural network outperforms the constituent quark model. The error is a factor of 3 smaller. Whereas for the baryons, the constituent quark model does modestly better, but we're comparable to what the quark model is doing. If you just take the input vectors to be the up quark, the down quark, etc., and you predict the mass based on the input vector, we find that you don't reproduce the masses in the constituent quark model. Neural network is in fact doing something else. Gaussian process gives an error of 13.5% of the mesons and 3.4% of the baryons. The error bars are quite somewhat larger. We can also predict with 79% certainty that the lightest baryon is the proton, and the second lightest baryon is a neutron in the plurality of cases. This is indicative of the machine learning aspects of the real world physics of QCD. Again, this is at n equals 3 colors. It's not a priori clear why these large n ideas should apply at n equals 3. The proton mass and the neutron mass are roughly degenerate. They're about 939 MeV. The predictions in the neural network, well, the actual value falls within the error bars. The error bars are rather large. The Gaussian process gives a sharper prediction closer to the actual measured result, but again, the error bars are rather large. In comparison, the constituent quark model is also roughly in the same ballpark for this. This is a technical point. Let me elide this point for the purposes of the talk. Okay, so pentaquarks are maybe 5 quark excitations that are discovered by LHCb. Again, with mesonic training, we're able to use neural networks and Gaussian process to predict close to the measured mass. The neural network does better than the alternative Gaussian process or the constituent quark model for measuring the masses of the pentaquarks. The data set of measured pentaquarks is really tiny, so it's very hard to extrapolate a lesson, but it's very nice that it's working. Tetraquarks, we don't actually know whether these resonances are in fact composed of 4 quarks. They could be excitations of mesons, in fact. And there are different composition hypotheses associated to the excitations that have been seen. And the excitations, I think not all of them are 5 sigma discoveries either. But the methods we've developed can, however, be distinguish these different composition hypotheses from each other. And we noticed that the tetraquark hypothesis performs less well than the meson hypothesis using our trained networks. In nuclear physics, there's something called the semi-empirical mass formula. This lets us take the number of protons and neutrons in a nucleus and predict the mass of the nucleus. You essentially capture volume effects, surface effects, effects of Coulombic repulsion, and various other things. And you come up with some formula that predicts the mass of a nucleus. We'd like to see such a formula for baryons. We like to take into account the effect of having an up quark, a down quark, a strange quark, an anti-charm quark, whatever, and with isospin, angular momentum, and so on. We'd like to come up with some formula. And the fact the neural network is working so well suggests such a formula might exist. It's going to be of a different character than semi-empirical mass formula because the physics is different in the baryonic case as opposed to the nucleon case. Nucleon case, the binding energy term becomes negligible as the number of protons and neutrons become large. In the baryon case, the interaction energy grows with n, so we can't formulate things in the same way. But this is the idea that there's a hope that such a formula exists. There's a question in the chat: have I tried predicting with baryons, training with baryons, and also predicting mesons? We've tried the full data set, but I think for purposes of understanding whether the structure at large n carries over to n equals 3, we focused on using mesons for training and baryons for prediction. The baryonic data set's also much smaller than the mesonic data set we've got. One thing we did notice was the anti-baryon masses are predicted to within 6% of the baryon masses without any a priori training to tell the machine that an antiproton should mass the same as a proton. It figures that out on its own. And in fact, for the fermions, the quantum number associated with the proton and the antiproton are different for parities instead of both fermions. And as well, the proton and the antiproton have a sign difference in isospin. The antineutron and the neutron have a sign difference in isospin. All of this is somehow intrinsic to the structure of what the network is learning. We're not teaching it these things. We're not requiring these things and demanding these things. The machine is just giving it to us. That's encouraging. Okay, so what's the physics here? Mesons have a mass at scale like 1/n. In real-world QCD, a perturbative parameter is 1/n squared, or some number over n squared. And perturbation theory works. Witten already noticed in the late 70s that this kind of picture may lead to an approximate decoupling of degrees of freedom. And 1/3 squared is like 10%. So you're getting things n equals 3 and n equals infinity may not be that far apart, in other words. Machine learning the Baryons spectrum from training on mesons is consistent with this picture. So for future work in this direction, we're thinking about glue balls. Glue balls arise as bound states of gluons rather than quarks and gluons. If you take so gluons transform what's called the 8 representation of SU3 and the adjoint representation. If you tensor together different 8s, 2 8s will have a singlet, 3 8s will also have a singlet. So like mesons and baryons, there may be some spectrum of glue balls that we'll eventually encounter in the electron ion collider and can compare to predictions based on some model that we may imagine. We can think about learning Regge trajectories. So the origin of string theory, the Shu-Fushushi dual resonance model, noticed that if you plot angular momentum against mass squared, you have a linear relationship. We haven't really looked at higher resonances so far. We've just looked at the basic mesons and baryons. So it'd be interesting to examine these higher resonances to see whether we can reproduce these Regge trajectories. There's something called the Gelman-Kubo mass formula. It's a hadron mass relation with strangeness or hypercharge and isospin. It's got certain coefficients in this formula. We can try to learn those coefficients. And then, these methods we've developed don't supplant the traditional methods of lattice QCD, where you put QCD on a lattice and study its behavior and take some continuum limit at the end of the day. These lattice QCD computations are famously involved and intricate. The calculations lengths are measured in graduate student years. So with a neural network, we're able to do these kind of things in minutes or seconds, in fact. So these new ideas in this QCD sector we're exploring with Orlin Kuchumbov, who's a second-year undergraduate at Oxford. My main collaborators in the QCD work are Yarden Gall at Oxford, Damien Meyer-LaPena, who's a postdoc at the WITS, and Challenger Mishra, who's at Oxford, soon to be moving to Cambridge. All right, so our analysis presents a fundamental challenge. How does a black box learn semantics without knowing any syntax? What might be useful to disentangle the answer to this question, we knowing what doesn't work. Unfortunately, people have a natural tendency not to publish their failed experiments. And a lot of what we're doing in applying machine learning in higher theoretical physics is trying a bunch of things and seeing what works and trying to explore whether we can understand the fundamental structure of what works. But it will be good to know what doesn't work. So at some point, maybe people in this community can come up with some database where you just list a bunch of things we tried that didn't work out. And then maybe there's some way to realize some dichotomous key that distinguishes what works from what doesn't. But we see that there are approximate functions the neural network is providing. In the case of knots, there's an f of j. Starting with the Jones polynomial, we can recover the volume of the knot complement. For the purposes of the QCD study, there's an approximate formula m as a function of the input, the constituent quarks and the valence quarks and some quantum numbers. So we'd like to find some analytic expressions. So far, besides just writing down what the matrices are and acting them on vectors, we don't have a detailed analytic expression for things, but that's what we're pursuing, and we're making slow progress in this direction. A bigger challenge is, can we use these technologies to do interesting research? There have been successes in this regard. In Go, famously, new opening sequences have been formulated by a machine that are superior to human opening sequences developed over centuries. In mathematics, at the level of a first-year graduate course in real analysis, computers are able to write proofs that a professional mathematician cannot distinguish from proofs written by graduate students in the course. So the state of the art in mathematics in real analysis is such that machines can do standard proofs. So far, they haven't invented new mathematics, but maybe one day that's possible. Indeed, Blavatsky was a famous proponent of using computers as proof assistants to make sure that one doesn't make mistakes in writing proofs. So when I started learning machine learning with Yang-Hui He and Brent Nelson, we started playing with the data set of the papers that appeared in our field. And papers in arXiv are, in physics, you can classify them in various of the subheadings, hep-th, hep-pH, hep-lat, so on. And simple training with, say, Word2Vec is able to categorize papers into the right archive based on the title with roughly 2/3 precision. And with 90% precision almost, able to distinguish formal papers from phonological papers just based on the title. Since we're working in some high-dimensional vector space using these methods, we discover syntactic identities between words. So, for example, Paris minus France plus Italy gives us Rome. King minus man plus woman gives us a queen. So if we apply these ideas to words that appear in our papers, we're able to discover real relationships. So a symmetry plus a black hole, there's some killing vector, some killing field that's in the game. Symmetry plus algebra gives us a group. Black hole plus QCD gives us a plasma. It turns out that QCD can be described at some limit by black hole physics. Space-time inflation. The universe is expanding. The acceleration is, there's an acceleration. The expansion is getting faster and faster. We think the end of this acceleration might be the cosmological constant, the energy density of the vacuum. That's a relationship that's embedded into the structure of this vector space. Finally, string theory plus Calabi-Yau geometries give us some compactification to four-dimensional low-energy physics. In fact, string theory, there are 5 string theories, 5 superstring theories, that are limits of a larger theory called M theory. And M theory on something called a G2 manifold, 7 real dimensional, M theory is 11 real dimensional, also gives us 4-dimensional physics. And machines are able to realize these connections. So hopefully, with the development of these technologies, we'll have the opportunity to work with machines and collaborate with machines and discover new physics. So thank you very much.
Yeah, thank you very much, Vishnu, for this very nice talk. Are there questions? Yes, Julia Norman. Yeah, please unmute yourself. Yeah.
Can you hear me well?
Yes, I can.
Well, first of all, thanks for this very nice talk. I just wanted to ask something basic. I think you already hinted at this a little bit. Have you considered applying interpretability tools to your neural networks? So, for example, relevance attribution methods that like really tell you what's important in the input for a certain prediction?
Yeah, this is exactly what we're looking at. With respect to knots, we're looking at things like Larrabee's relevance propagation in order to figure out which details are picked out by the network.
Okay, thanks. Yeah, that seems like a perfect fit for your application. Yeah. So I wanted to ask. Thanks.
Further questions? So maybe let me ask a question. So in predicting meson and baryon masses, have you got a hint at the formula that the neural network is approximating? Like, I mean, you can like, fit some, make some ansatz for the function and see. And if you
looks like
this, can you can you give it a phenomenological interpretation as well?
Not so far. We're thinking about this. It seems like the important things are charm, bottom, and isospin. And the other things are less important. So whatever formula we invent would have to maybe focus on those things. Somewhat of the problem here is that the data set's rather small. We've got 196 mesons, 43 baryons, I think. So it's hard to, it's not a large data set we've got. Unfortunately, those are the particles that have been discovered. So it's hard to say what the formula might look like. The number of isotopes is rather larger than the number of hadrons that we've seen.
I see.
Also, the formula for the semi-empirical mass formula is structurally simpler, maybe, than non-perturbative QCD.
Question? Yeah, I have a question.
Yes, please.
So with such a small data set, did you have to do anything special to avoid overfitting? That's usually what the first problem you have with very small data sets, that you have massive overfitting. You have zero error on your training set, and then you have huge error on your test set. So did you do anything special to avoid that?
Not really. It turns out that in our case, the inputs don't have a unique output. So knowing these vector inputs doesn't specify a mass uniquely, because different particles can have the same quark composition and quantum numbers. That might be an inherent mitigation towards overfitting.
I see. You say it's a kind of regularizer because it's the same as having a little bit of noise, which is a kind of regularizer.
Yes.
Okay, thank you.
Any more questions? Oh, there's a new message. So you were hinting at, say, improving chiral perturbation theory. You have something in particular in mind, or is this?
No, this is just a dream. But the hope is that if you can understand, aspects of QCD better, maybe your effective field theory for Baryons improves in the process. But I don't have anything concrete to say there. Another thing to do might be to import lattice results as well. Maybe using lattice simulations as additional training, and will be a way to make progress in understanding aspects of QCD better, at least phenomenologically.
I see. So final chance. So, okay, I cannot see any more questions coming up. So, yeah, I'd like to thank Vishnu again for a very nice talk. And I hope to see many of you in 2 weeks' time again for Physics Meets ML. Okay, bye.